Hello, welcome to the first lecture of the series An Engineering View on Avionics, Navigation and Aircraft Control, elaborated and narrated by me, Ítalo Romani de Oliveira. This lecture is the first of two on the topic of civil aviation radio navigation systems based on ground stations. Let us start with a brief motivation about the subject. In which transportation means do you think that the radio navigation did first arise? Was it in the aeronautical? Was it in the maritime? Or was it in the terrestrial? Well, it happened to be in the maritime. And why so? In the primordial of radio navigation, the equipment was large and heavy, and ships were the only vehicles capable of being adequately equipped with it. And the maritime navigation really has a clear need of orientation because of the long distances, because of the absence of visual references, and because of the need of navigation at night or under fog. With time, the equipment became more compact and light, while at the same time the aircraft became more robust, which permitted installing this navigation equipment inside them by needs similar to the maritime navigation. Furthermore, the aircraft kept increasing operational speed and altitude, what made more difficult the navigation by visual means, and turned aircraft highly dependent on radio equipment. But there is yet another important reason for the utilization of radio navigation in aviation. We are talking about air traffic control, or shortly ATC, which allows sharing the airspace among multiple aircraft without collisions. In order to keep aircraft safely separated, ATC distributes them through predetermined routes and with adequate spacing. The definition and execution of these routes depended, for several decades, on the radio navigation systems based on ground stations. Despite the fact that this dependency has been significantly diminishing in the last years, with the utilization of satellite-based radio navigation, the ground-based radio navigation will still continue to be used for a long time due to compatibility with old aircraft and to the possibility of satellite signal outages, either locally or globally. Now, let us see the main equipment types which can be considered as radio navigation. These types can be classified in affinity groups. The first of them is called here autonomous navigation, because it does not depend on the complementation of any device not belonging to the aircraft. Inside this group, we have the so-called Doppler navigation, which is performed by the emission of radio signal from the aircraft towards the ground and by the processing of the corresponding echo. Depending on the aircraft velocity vector, the reflection point on the ground receives a signal frequency different from that emitted at the source because of the Doppler effect. And when the signal returns to the aircraft, this frequency shift will be measured and can be used to estimate the aircraft speed in relation to the ground. But because of a few reasons, this technology is very little used nowadays. In the same group of autonomous radio navigation, we have the radio altimeter, which measures height of the aircraft relative to the ground by means of the signal echo. And also in the category of autonomous radio navigation is the airborne radar, normally used to detect storms, but in some cases capable of helping in obstacle detection. Proceeding with this classification, we have a large group of equipment types which depend on remote stations, be them on ground or in satellites. The first to arise were those based on ground stations. As you can see, there is a long list of types in this category, some of which we will see in detail in this lecture. Finally, for contextualization, there is the category of equipment whose reference stations are in satellites. Inside this category, the first member to be developed, and the only one which currently works fully, has the name Navstar, but is popularly known as GPS, Global Positioning System, which has origin and ownership in the United States of America. Besides it, there is Galileo, which is the European system, and GLONASS, which is the Russian one. Both Galileo and GLONASS are still incomplete and facing uncertainties. But even having only Navstar working, the satellite-based navigation is already extremely important for aviation, so an entire lecture will be dedicated to it. As these technologies form a vast theme, they will be explored along a few lessons. This lecture in specific talks about the first two items of the list in the middle, ADF and VOR. And what is ADF about? First, the meaning of this acronym is Automatic Direction Finder, a kind of self-explanatory name. It constitutes the first technology to spread in its category, being the simplest and still very popular these days. To understand how it works, let's observe the illustration. Here we start with a fixed station transmitting electromagnetic waves. As taught in physics classes, an antenna energized by an oscillator emits waves which propagate through the surrounding means. The direction and sense of wave propagation are here illustrated by the vector C. The electric field associated to this wave manifests itself perpendicular to the direction of propagation, as illustrates vector E and others parallel to it. The magnetic field, not shown here for simplicity, is perpendicular both to E and to C. The variation of the electromagnetic field caused by the wave will induce an electric current in the receiving antenna, with some special feature that we will see here. We are considering this antenna with a shape of a planar loop, positioned perpendicularly to the vector C. With this positioning, exhibited in this figure, there is no difference of electromagnetic field among the distinct parts of the antenna. Being so, the electric current induced on it is null. However, the attitude of the antenna may be rotated and form certain angle theta in relation to the direction of wave propagation, away from the 90 degrees being displayed on the figure toward another angle. As theta varies, the intensity and direction of the induced current also vary, according to the graph on the right. When theta is equal to 0, that is, the plane of the antenna is aligned with the wave direction, one obtains the largest possible variation of the electromagnetic field, and this way, the modulus of the signal in the antenna is maximum. As theta increases, the modulus of the received signal diminishes, until theta reaches 90 degrees and the signal vanishes. In the case theta continues to increase, the modulus of the antenna signal will also increase, but its sign will be inverted. That is, there will be a phase change of 180 degrees in the antenna signal when passing by theta equal 90 degrees. And if theta continues to increase, the variation captured in the antenna signal will happen according with the remaining of the graph. Being so, it is important remembering the following points. First, that the signal received in the loop antenna will have maximum intensity when the plane of the loop is aligned with the direction of wave propagation, that is, theta equals 0, or pi. And the same signal will have minimum intensity, that is, 0, when the plane of the loop is perpendicular to the wave direction, that is, when theta equals pi over 2 or 3 pi over 2. Very good. And how can we use this antenna to guide the navigation of an aircraft? For answering this, let us think of what would be easier, to search and maintain the maximum signal intensity, or to search and maintain the minimum signal intensity. Which one would be best? And the truth is that it is easier to work with the minimum signal intensity. In order to know the reason for this, we can look at the graph on the right-hand side figure again. One of the things one can notice is that the minimum signal intensity is 0. When we speak about intensity, we are talking about a concept of an unsigned quantity. That's why the minimum intensity is 0. It cannot be negative. Anyway, when it is 0, its gradient is the most accentuated. That is, there occur faster variations, and these variations serve to constantly help the antenna orientation to maintain it perpendicular to the direction of wave propagation. Therefore, the angle theta of the antenna can be used to adjust the direction of the aircraft in relation to the transmitting antenna. In case the loop antenna is rigidly fixed to the aircraft, it is possible to adjust the aircraft heading during navigation so as to be oriented towards the transmitting antenna. But this basic idea presents various flaws, as it will be seen next. The first problem which arises from maintaining the antenna fixed is the need of flying with indirect heading, due to the wind direction. Any wind vector not fully aligned with the navigation vector will have a transversal component, which makes the aircraft to be misaligned. If the antenna remains fixed, it accompanies the same misalignment, so it will not be possible to maintain the signal null in order to regulate the navigation course. Also, if this problem is not solved, it is not possible to navigate in any line which does not pass exactly over the station. And what solutions were developed for this problem? The first is pivoting the antenna, so that the rotation of this antenna can be controlled from inside the aircraft, either by a human operator, as it was in the beginnings, or by an automatic system. Here, in this figure, we see the casing of a navigational loop antenna, which works by the principles we are studying, installed below the fuselage of a DC-3, a famous transport aircraft created in the 1930s. Inside this droplet casing, the antenna rotates to find the direction of navigation. There are also other configurations in which the antenna is fixed, but in these cases, the signal captured by it is conducive to a coil system inside the aircraft, which is capable of producing a rotation equivalent to what would be the rotation of the antenna. This type of system is known as Bellini-Tosi, and since long fell into disuse. The modern solution for the indirect heading is to use a set with a few antennas which remain fixed, feeding a circuit with modern electronic components capable of determining the signal direction by means of phase differences, without necessity of rotating the antenna. We will see an example for this ahead in this lecture. Before that, though, it is important to know another problem which arises when using the basic principle of the loop antenna. It's what we may call double sense. What does it consist in?
consists in the fact that, with the lack of a reference signal, it is not possible to know whether the aircraft is moving towards or away from the antenna. In order to know the explanation for this fact, let us observe the figures of the example. In the first figure, the transmitter antenna is on the left and the receiver on the right. The sense of wave propagation is indicated by the little arrow. In the receiving circuit, a sinusoidal signal similar to the space wave is observed. As there is no phase reference, the only quantities known are signal frequency and intensity. If the situation becomes inverted, according to the second figure, despite the wave propagating in the opposite sense, it is impossible to distinguish the situation on the bottom from the situation on the top, unless two or more antennas are used simultaneously. But for this, another antenna type will be used, called dipole or linear. The loop antenna is called monopolar because it's formed only by a single continuous element. In case the dipole antenna becomes perpendicular to the direction of propagation of the space wave, it will serve as phase reference to the signal on the loop antenna. When the disposition of the antennas in relation to the wave is according to the top case, the phases of the signals received in both antennas are the same. Here, it can be said that the electric currents observed in the measurement elements have the same sense. But if this disposition is flipped, as in the case depicted on the bottom, the signals in the respective antennas become out of phase by an angle pi or 180 degrees. Observe that, in both cases, the signal in the dipole antenna remains unchanged, and this is the key fact being used here. In case the dipole antenna becomes fixed in relation to the monopole antenna, it is possible to distinguish when the transmitter station is on the one side or on the other. This is already a great advance. But is it true that, with this configuration, it's possible to completely determine the navigation direction on the plane? Well, still not. And why? We'll see now. The problem, which still exists, can be explained by the simple formula. The cosine of theta is equal to cosine of minus theta. This makes that the transition between these two cases presented here, whose difference is 180 degrees, be indistinguishable when it is done by one side or by the other. I mean, when doing a 180 degrees rotation, be it to the left or to the right, the final result is the same, but there will be different intermediate situations. In order to define this problem in a more exact manner in the case of the antenna, we recur to a gain diagram. In this diagram, the plane of the screen represents the horizontal plane tangent to the surface of the Earth. The x-axis, shown here in the vertical direction, represents an axis on the plane of the loop antenna, and the y-axis, displayed here on the horizontal, represents an axis perpendicular to the plane of the loop antenna. The dashed curves represent the gains of the individual antennas, and the continuous curve represents the sum of the gain of the two antennas. Taking a point in one of these curves and tracing a straight segment between this point and the origin, as shown by this inclined line, the size of the segment represents the signal gain at the antenna output, and the angle between this line and the x-axis represents the angle that the plane of the loop antenna is forming with the transmitter station, projected on the plane tangent to the surface of the Earth on that point. When this angle varies, the compared gain between the antennas changes. Remembering that the term gain refers to the modulus of the received signal. Okay, now let's concentrate our attention on the dashed lines. When the angle theta is 0, we have the point where these lines cross the x-axis on the positive semiplane. On this point, we say that the gain of the signal is c, lowercase c, as observed together with this measurement arrow in the figure, and the gains of the two antennas coincide. The large circle refers to the linear antenna, and the small circle refers to the loop antenna. The formulae of the gain variation in function of theta are presented here. To the linear antenna, the gain R is constant and equal to C. To the loop antenna, the gain varies according to the formula R equal to cosine theta. In truth, the antennas are designed so as to that their gains coincide on the points where theta is 0 or 180 degrees. When theta is 180 or P, we are talking about the point on the inferior extremity of the graph. Besides the difference of theta, there is yet another difference represented here. According to what I had mentioned, the signals of the electric current measured in the receiver may be equal or opposite. On the positive semiplane, these currents have the same sense, hence the 2 plus signals. But, as we had seen in the illustrative example, the signal of the current measured in the linear antenna remains the same, that is, remains positive, despite that, on the right-hand side diagram, the larger circle is drawn on the negative semiplane. In truth, the difference between the superior and inferior semiplanes is that, on the superior, the signals of the currents are equal, while in the inferior, the signals are opposite. But, in the end of the day, we want to know what happens with the sum of the two antenna signals, which is represented by the continuous line. Summing the two equations, we obtain C times 1 plus cosine theta, and as we are talking about the sum of the two signals, there are no longer two distinct signals, but just one. Thus, the only variation happening here is of theta. When theta is between minus 90 degrees and plus 90 degrees, the gains of the two individual antennas sum up, and then we obtain the profile of the continuous curve on the superior semiplane. On the other hand, when theta leads to the inferior semiplane, the gain of the loop antenna is subtracted from the gain of the linear antenna, yielding the profile of the continuous curve in the inferior semiplane. The whole continuous curve, then, acquires the shape of a heart, hence the name cardioid, used for this type of curve. Right, and how the cardioid can be used for determination of navigation direction. First, it is important to observe that the cardioid is symmetrical from the left to the right, that is, in the horizontal direction. And now, let's take one of its sides, for example, the left side. It is possible to observe that, for each gain value, there is one and only one value of theta. So, from this gain, it's possible to obtain the navigational theta, right? Right, but because this determination is done only at one side of the curve, theta can vary only between 0 and 180 degrees. And so, we have exhausted the power of the method of two antennas. Because the cardioid is symmetric from left to right, it is not possible to distinguish on which side is the angle theta. So, what would be the solution for this? The solution consists in adding one more loop antenna, forming a set of 3 antennas. The illustration we see here is of one antenna for maritime navigation, using the principles which we are studying. We have in this set 2 loop antennas, disposed perpendicularly to each other, and a linear antenna. In truth, if we observe the picture more attentively, there are 2 linear antennas in it, but only one of them is used in the navigation system under study, the one which is seen closer to the loop center. With the 2 perpendicular antennas, the phase difference between them allows to resolve the problem of hemisphere determination, which I was just explaining. Anyway, it would be inadequate for an aircraft to use such an awkward antenna. In modern aircraft, it is possible obtaining the same effect of these antennas in a configuration much more aerodynamic, with the help of modern components. The illustration on the right shows the newer antenna set according to the same method, but in a much more compact, flatter configuration, protected by a cover. The loop antennas can be identified here, forming a cross, and the sense antenna is a little board extending longitudinally in a discrete way. It is important having into account that such configuration with 3 antennas does not need to be mechanically rotated to find the direction of the transmitter antenna. Why so? Because by the observation of the phase difference between the perpendicular antennas plus the information originated in the sense antenna, it is possible to univocally determine the direction of signal arrival. However, the complete automation of this detection in 360 degrees requires an electronic circuit which is not completely trivial. That's why it took a certain time until arriving to the equipment similar to what we have nowadays. And from the moment when this process became automatic, it was given the name Automatic Direction Finder, or ADF for short. However, we often hear the term NDB, which means non-directional beacon, but that, in truth, refers to the transmitter antenna for this system. And, as I have mentioned the transmitter antenna, let's enter a little bit into this topic. Here, we see an antenna which transmits the signal used by the ADF. Initially, there were no exclusive stations for ADF, and the commercial AM stations were used, since every town had one. But this was a problem because, if an air route passed overhead desert areas, as it often happens, there would be no signal available. Besides, a commercial station does not provide reliability and availability levels necessary to air navigation. Because of all this, the countries created station networks dedicated to the air navigation, and from that moment, these stations have been called NDB, non-directional beacon, a somewhat controversial name, but which stuck. 2 frequency bands were reserved for the NDB stations, below the commercial band, which are the low frequency, or LF, between 190 and 515 kHz, and the band medium frequency, or MF, between 510 and 530 kHz. Besides the main sinusoidal signal, the transmitter station modulates it to send along, in Morse code, its identifier of 3 characters. With the adequate equipment, the signal can be heard by the pilot, although modern equipment processes this information automatically and show it to the pilot in a digital display. In the left-hand side figure, we see that the Campo de Marte station has the identifier Mike Alpha Echo, and its base frequency is 260 kHz. This label was obtained in a navigation chart, as well as the round symbol on the bottom, which marks geographically the NDB. This type of symbology is used in the charts used by the pilots to orient their route. And as we are talking about the interaction with the pilot, let us see now the typical displays for ADF navigation. In the first figure, we have a very simple gauge with just one pointer and a fixed scale. This fixed scale is associated to the aircraft longitudinal axis, and the pointer is the direction determined by the ADF in relation to that axis. Things being so, the resulting information is relative to the aircraft longitudinal axis, not to the north. In order to know the angle of the aircraft heading in relation to the magnetic north, it is necessary to consult the compass. But this was just the beginning, because there are much better gauges, as we are going to see now. This gauge on the left integrates several information items in just one place. First, the angle scale can be rotated according to the zero chosen by the pilot, which may or may not be the magnetic north. Besides, we have a yellow and a green arrow in the central area of the gauge. These arrows correspond respectively to each of the switches on the bottom corners. We see that these switches allow selecting the modes ADF or VOR. In the case presented, both have ADF selected, meaning that each arrow in the gauge exhibits directional information relative to a station in a certain frequency, aiming at pointing to distinct stations. In order to tune to the desired station, the pilot has tuner buttons and displays located on the central section of the cockpit, as shown in this figure. The idea of tuning to different stations is that, being the locations of the stations known, it is possible to know the intersection points of the lines between the stations and the aircraft, and find the point which determines the geographical position of the aircraft, even if with low accuracy. This is called ADF-ADF or NDB-NDB navigation, and allows for the execution of arbitrary routes, which don't need to pass overhead the station. Besides all this, the same gauge can be used by the VOR system, which is the second navigation system which we will study in this lecture. Indeed, the pilot may use here any combination of these two systems. May use just one station, be it VOR or ADF, may use also two ADFs, two VORs, or ADF and VOR combined. Each of these modes has some operational differences, but all of them are possible. The VOR, just mentioned, is a system which was created to resolve some typical problems of the ADF NDB system, which we will study now. The first problem observed with ADF NDB is that of ionospherical reflections. Signals in low and medium frequencies are significantly prone to kick on the ionosphere and come back to the ground. But why is this bad? Well, mainly because this generates multiple signal paths, which, in the reception point, cause destructive interference in the signal, actually damaging quality of the signal. That is, there appear two or more signals arriving at the same point with the same frequency, same origin, but out of phase, and this generates spatial irregularity in the resulting signal. Another problem is that of coastal reflection, which occurs because of the following fact. The low signal frequencies make that the signal waves propagate through the ground layers, and when there is an abrupt element transition, refraction happens. This is exactly what happens when the wave passes from Earth to water and vice versa. As you probably know, the refraction causes a change in the direction of wave propagation, and when this occurs along a coast of irregular contour, this results in several distinct signal directions, hence multiple signal paths.
Another source of problem is the shape of aircraft body and wings, which may obstruct the signal or generate even more multiple paths. And finally, there is a large variety of interferences exogenous to the signal, such as electric, cloud activity, and solar radiation. In a certain manner, these phenomena may be forecast, but hardly can be impeded to interfere with the NDB signal. Joining all these problems with the intrinsic characteristics of the ADF technology, one finds in practice a net error of 5 degrees in the determination of direction, which is considered high. In order to correct this lack of accuracy, the pilot may look out of the window and do a visual recognition of the surroundings, but this is not always possible. If, on the one hand, ADF is a cheap and simple technology, its error magnitude may be really problematic in several situations. Because of this, other radio navigation means emerged, among which I picked one, the VOR, to talk about now. The name VOR comes from VHF, omnidirectional range, and has two main differences in relation to the ADF. The first one is the frequency band, said VHF, with a little more than 100 MHz. The other difference is that VOR possesses two fundamental signals, a signal constant in all directions and a rotating signal. The dephasing between the constant and the rotating signals allows the univocal determination of the receiver's azimuth on the plane tangent to the Earth's surface. The VOR reminds of the maritime light beacon, which remains rotating, but is still a poor analogy. Let us see then the real working principle of the VOR. Well, the first item to be commented here is about the transmission frequency between 108 and 117.95 MHz. This frequency band makes that the signal be not reflected on the ionosphere and be not propagated through the ground, resting only the line of sight for it. This eliminates considerably the phenomenon of multiple paths. Although there still occur reflections on the terrain, the final result is more robust to interferences than possible with the NDB signal. And, as I mentioned, there are two VOR signals. What happens is that, over the base carrier frequency, the station transmits two modulated signals. The first one, the omnidirectional reference signal, which is uniform in all directions, and the second one, which is the rotating or directional signal. In the first VOR generations, the rotating signal was generated by a mechanically rotating antenna, hidden inside the white radome over the shelter, which is being shown in the picture. The rotating antenna intensifies or attenuates the main signal in the direction to which it is oriented, making that receivers at different directions see signal pikes in different moments or phases. We may understand this principle by means of another figure, which we will see now. So, in this figure, we see the VOR signal modulation. The example shown here is known as conventional, because it represents the first VOR version. The waveform illustrates the signal seen by the receiver. The carrier frequency, around 110 MHz, is illustrated by this pattern of parallel lines in the central area of the wave. This carrier has a solid border, which appears because of a subcarrier of 9960 Hz. This subcarrier causes an amplitude difference corresponding to 30% of the total amplitude variation of the main carrier, and is then modulated in frequency to transmit the omnidirectional signal. That is why we perceive that the distance between the peaks of the saw is smaller on the extremities of the figure than in the center. The repetition period of this frequency variation corresponds to the frequency of 30 Hz and is seen with the same phase, whatever the azimuth of the receiver in relation to the transmitter. But, as I said, there is another signal being transmitted here. Observe the dashed line which represents the mean path of the saw border. This is the mean amplitude between neighboring peaks and valleys on the saw. Observe as well that this mean line has also a periodic variation, corresponding to 30 Hz, with an amplitude variation corresponding also to 30% of the variation of the main carrier. And, from this point, we can understand why to use these signals for determination of navigation azimuth. It is defined that when the frequency peak of the omnidirectional signal coincides with the amplitude peak of the directional signal, situation corresponding to the figure, the azimuth between receiver and transmitter is zero. And, in the extent that the receiver changes azimuth, there will be a dephasing between the signals, which varies in the range between 0 and 359 degrees, corresponding to the geometric azimuth, which allows guiding the navigational course of the aircraft. This is the basic working principle of VOR. However, there are additional elements to complete the VOR system. One of them is a signal of 1020 Hz in the same carrier, used to transmit the station identification characters. The convention follows a standard similar to that seen for NDB, with 3 characters transmitted in Morse code. Some examples are presented here: CGO for Congonhas VOR, CPN for Campinas, PSN for Pirassununga, etc. Besides, the identification may be transmitted by voice signal, and the voice may be alternating with the Morse code. This facilitates the verification of the station at any instant. Anyways, this technology suffers from some limitations, as any technology. Despite having reduced considerably the problem of multiple signal paths and interferences in relation to ADF, the multiple paths still persist because of reflections on the ground surrounding the antenna. The rotary antenna is not capable of a very coherent beacon, having some spreading, which in turn causes ground reflections. In order to correct this problem, an array of multiple fixed antennas can be used, with which an effect similar to rotation is achieved, but with a much more coherent beacon, which does not hit terrain, but only goes to the airspace. Another measure to be taken is to invert modulation, making that the directional signal be modulated in frequency, while the reference signal in amplitude. This allows a greater signal quality than that of the conventional VORs. It soon appears the so-called Doppler VOR. This name comes from an analogy made with the Doppler effect. In order to understand how the Doppler VOR works, I'm going to explain it here in a comparative way in relation with the conventional VOR. First, let us see this animation representing the conventional VOR. Here, the colored elements represent the frequency modulation, while the gray shade elements represent the amplitude modulation. The linear bands outside the circle represent the signal received at different azimuths. If we observe with attention these bands, we will see that the signals in the respective colored bands are all equal, while the signals on the gray bands have different phases. This represents the fact, previously seen, that there is signal modulation in frequency generated by the fixed antenna, which has the same phase in all directions. And there is also a signal modulated in amplitude, generated by the rotary antenna, with a fixed focal point in the center of the circle and having only the effect of attenuating or amplifying the amplitude of the main signal. Now, let's compare this animation to that one corresponding to the Doppler VOR. The first great difference is that the focal point of the rotary antenna is not in the center of the circle. In case the rotary antenna emits a signal with constant frequency in this configuration, the same signal will present variable frequency in the receiver because of the Doppler effect caused by the resulting longitudinal velocity. This is why here the modulation of the rotary signal occurs in frequency, contrary to the conventional VOR. This can be considered an advantage, because the frequency modulation is more robust to interferences, providing a higher signal noise rate. And the omnidirectional signal in the Doppler VOR is produced by the amplitude modulation of the main carrier, represented by the gray elements of the figure. When observing the reception bands in the Doppler VOR animation, we can notice that the signals on the respective colored bands, which correspond to the signal modulated in frequency in the antenna, are dephased, while the amplitude modulated signals corresponding to the gray bands are always in the same phase. However, in practice, it is difficult to implement a rotary antenna of such type, so to provide a good signal quality with the necessary power. Remembering that the signal has a 30 Hz frequency, so the antenna would have to rotate at 1800 RPM with certain rotation radius which produce the correct modulation. That is why it's preferable to generate an equivalent signal by means of a circular array of fixed antennas, which you will see now. And here we have the Doppler VOR antenna array. We observe in it a circle of white antennas over the metallic plate. Each of these antennas is designed to direct the signal to the airspace, not to the ground. Even though the great metallic plate, which may have some tens of meters, contributes to the VOR signal not to spread to the ground and have a coherent propagation cone, oriented upwards. These antennas are activated alternately, with certain phasing, so as to simulate the rotary VOR signal. This manner, there is no mechanic wearing, and the signal coverage becomes much more uniform, greatly reducing the problem of ground reflections. So, now I will talk about the operational range of this type of equipment. Its range is majorly determined by the curvature of the Earth, since the VOR frequency depends on direct line of sight between the transmitter and receiver. This figure illustrates well the limitation of the line of sight due to the horizon. If the relative position between transmitter and receiver is below the horizon line, it is not possible using VOR. As it can be deduced from the geometry shown here, the altitude of the aircraft must be taken into account. Being so, it is possible determining the approximate operational range of the VOR using the following formula. Distance d in nautical miles is equal to 1.1 times the square root of the altitude h in feet. This constant 1.1 appears both because of the unit conversion from feet to nautical miles and because of the Earth radius, which enters in the equation. In order to have a notion of the numerical results of this formula, observe the range table here presented. See that, at low altitudes, the range is considerably small. In the last row of the table, we see that, for an altitude of 20,000 feet, the operational range is 141 nautical miles, and the table finished there in purpose, because VOR is not capable of being operated distances much greater than this. What happens from that distance on is that the power of the signal received becomes too small and, because of this, not reliable. But within this operational range, a well-calibrated VOR system provides an accuracy around 1 degree, which is substantially better than the accuracy of an ADF. And so we conclude this lecture. In summary, these were the topics that we saw. First, the origins of the navigation by radio systems. Second, the main types of radio navigation. After this, we saw the navigation by the ADF system, which operates in low and medium frequencies and has an accuracy of around 5 degrees. And finally, we saw the VOR navigation, both conventional and Doppler, which operates in the frequency band denominated VHF and has an accuracy of around 1 degree.